I do want to spend the last 3 minutes reviewing binary search. Today I was hoping to start analysis of algorithms with some more recursive examples, but I may not get to it. In any case, the kind of recursion that will be on the exam is the kind of recursion we've already done, more examples of the same. The analysis part will not be on this exam, so this is fine. I want to have you recall our binary search algorithm, which you recall was intended to search a sorted list or a sorted structure, sequence of elements. And what the purpose of this, that structure here is a list L, and I'm looking for an element that has value X. And what I want to return here is the value of the index for that element. Now, what differentiates this from the index sequence method is that here we know that this list or sequence is in sorted order. It has an ordering from small to large. The function is recursive, meaning that the function call is defined in terms of itself. But this recursive structure is a little bit different than sort of the simple ones we did for factorial. We have a function definition. Binary search takes the sequence and the item we're looking for. And then there's an embedded definition of this helper function. And you recall that the embedding was there just to keep that helper function secret. Nobody can use it except if called from within my binary search function. And in fact, inside binary search, the only thing we have is a helper function definition and then a return statement that invokes that helper function. That's it. If we look at this, the helper function is returned with the index 0 as low, because there's two arguments, low and high. 0 is low, and the length of L, which is one beyond the last index, is high. And you'll notice that inside the helper function, not only am I using the variables low and high, but I'm also accessing this variable L, the list itself. And I can do that because this function is embedded inside the scope of the other function. So all of the parameters that are arguments to this outer function, whatever values they have within the function itself, are also available within the helper function. If you looked at the previous slide from the other day where the helper function was separate, the helper function had 4 arguments. They were L, X, low, and high. But now, because these are the parameters of the outer scoping function, these can all be accessed directly from within. So this is a very common structure. Using a helper function to sort of parcel off some little bit of algorithmic behavior that you can define separately is handy. When you're doing incremental development, you would develop this function separately and test it separately. And when you were confident it works, you would embed it inside the helper function, inside the original function. So looking now at the recursive helper function, there are 2 arguments. I compute mid, which is the average of those 2. That gives me the pointer in the middle. And then here is the recursive part of the function. There are 2 separate base cases and 2 separate recursive steps. The base cases are tested before the recursive steps, which is important so I can exit the function. And here, you'll notice that each recursive step, which sort of separates the space, the reinvocation or the recursive reinvocation of helper has arguments that are different from the original invocation. And that difference, which essentially reduces the range to either the lower half or the upper half of the original list, continues to make progress towards one of the base cases. The conditions that give it the base cases are when we run out of lists because we've cut it all away. And so since I'm making the list shorter all the time, eventually I'm going to get there. So that is the heart of our binary search function, and we'll stop here, and we'll pick up our discussion of recursion next time.